In today's class, we are going to learn about maximum likelihood estimation, also called as MLE in machine learning. So before we start, okay, we will first start with an analogy. Analogy is nothing but it's a story where we will understand the core concepts of MLE without involving the mathematical part first. So we'll first understand how and why we do it, and then we will get into the maths part. Okay. So MLE is little max heavy and statistics heavy, to be honest. So don't be overwhelmed. Just follow along. Just try to answer the questions that I ask, and I think you'll be more than enough. You'll be good to go. Okay. So let's start. The analogy. Okay, you are a cookie detective. Okay, so since you're all computer science majors, you don't have to think of cookie as the cookie in your browser, not that one. It's a normal cookie, a biscuit. Okay, you're a biscuit detective. So what we are going to do is, you enter a kitchen. Okay, and in the kitchen there is a plate. Okay, there is a plate. In this plate there are 10 cookies. How many are there? 10 cookies are there. Let's draw 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. There are 10 cookies, out of which 7 cookies are chocolate cookies and 3 are butter cookies or butter biscuit. Okay, so let me take another color. Okay, so 7, right? So, and yeah, so 7 are, the ones in yellow are chocolate, and the ones in red, the circles are butter. Okay, so out of this, they are hot, they are hotly made, they are served to you in a plate, and you see it. Now there are 2 friends of yours. Okay, so friend A loves chocolate cookies. Okay, and there is an 80% chance that the chocolate cookies were made by A. And there's friend B who likes a lot of variety, so loves variety of cookies, and there's a 40% chance that it was done by B. Now I am giving you this question. Tell me, what is the probability, okay, that the 7 cookies, the 7 chocolate cookies were made by A or by B? How will you find this out? Okay, just think of this intuition. Okay, so you might have come to some conclusion. So if you said the answer is A, friend A made the chocolate cookies, yes, you are right. So how does a computer answer this question? How does a computer come to the conclusion that this 7 cookies could have been made by friend A, not friend B? Well, there is a chance that friend B could have also made it. So let us start with the analysis of the mathematical part. Before mathematical part, let us go step by step. Okay, let's assume that friend A baked them. What is the likelihood of getting 7 chocolate chip cookies and 3 oatmeal cookies if probability is 80%? Yes, that's the question. And let's assume B baked it. So what is the likelihood that getting the same 7 cookies and 3 oatmeal cookies with a probability of chocolate chip cookie only 40%? So intuitively, the batch of 7 cookies, chocolate cookies and 3 oatmeal cookies seems more likely. This is the word that is to be noted. More likely have come from friend A, who's a chocolate chip lover. Okay, I'm not saying that A made it. I'm saying that it is more likely that A made it than B. Okay, so this is the concept of maximum likelihood estimation. I am estimating what is the maximum likelihood of an event to have occurred. Okay, so in this case, the cookies, the 10 cookies are our observed data. Let me change the pen color. Okay, so the 10 cookies are our observed data. And you want to find the parameter. What is that parameter? The probability of baking a chocolate chip cookie. Okay, by who? The model. We have two models here. Model A is friend A, who likes chocolate chip cookies, and B, who likes variety. So 80% and 40% is the model. Okay, that makes the data you observe the most probable. Understood? Okay, so we have understood the basics of what MLE is all about, maximum likelihood estimation. Let me give you a normal example. Okay, let us say there's you and your brother. Okay, you are 5 foot tall and your brother is 5 foot 6, 5 foot 6 inches tall, and there is a vase that is kept 6 feet above the ground on a shelf. Okay, you both are playing in the hall and this vase is broken. So now your mother comes and you are saying, I didn't do it. And your brother is saying, I didn't do it. So now your mother is trying to identify who could have done it. Your mother knows that your brother is taller. So the likelihood of him doing is more than the likelihood of you doing. That doesn't say that you might have not done it. Okay, but the likelihood, the maximum likelihood estimation is more leaning towards your brother because he is taller. So this is called maximum likelihood estimation. Okay, so where do we use this? So MLE is the backbone of parameter estimation in ML. So whenever you are maximizing the probability of data or minimizing negative log likelihood, we will learn about what negative log likelihood is, or cross entropy, you're doing an MLE. Okay, so where is it used? So in neural networks and probabilistic models and generative models. So all your LLMs use this MLE for maximizing the probability of your data. So okay, let us start and get into the cases. Okay, these are the edge cases in our MLE problem. So okay, first case is you found one cookie. Okay, if you only found one cookie and it was a chocolate chip cookie, would you be certain about who the baker was? Okay, so this talks about the idea of sample size and confidence in our estimate. So just read it and keep it in your mind, and when we are doing the mathematical formula of it, the derivation of it, you will understand why we are talking about this. And next is, what if all 10 cookies were chocolate chip? Which friend would you suspect then? How confident would you be? Okay. What if you found 5 chocolate chip cookies and 5 oatmeal cookies? What would you think? Who would you think is more likely the baker? Okay. And what if we didn't know the exact percentage of each friend? So now we know it's 80 and 40. So what if we want to find out who's more likely, the underlying probability of making a chocolate chip cookie, given that 7 were chocolate out of the 10. Okay, so we will discuss all these specific cases and why I have asked these questions right now. But you will understand, like you would have understood the question, and you can also think of the edge cases. So as we go on, we will discuss more about it. Okay. Okay. So the mathematical idea. So firstly, to understand the Bernoulli trial, So Bernoulli trial is nothing but it is an experiment which can only have two outcomes. Okay, it is like tossing a coin. Okay, and it is like on a good day, like let's say there's no rain or there's no issues with the match. There is only two things that could happen. It's either a win or a lose in a match. So a cricket match always ends in a win or a lose because there's a concept of super over. So yes, understood? So success, this event occurs with the probability P, and failure occurs with the probability of 1 minus P. Okay, I hope you understood what Bernoulli trial is. Now, the core idea of MLE is to find the parameter value for a model that maximize the likelihood of the observed data. What is the parameter values of a model? Here, in this cookie problem, we have found out that 0.8% or 80% is the parameter or the value by which friend A could have baked it, and 0.4 or 40% is by which friend B could have baked it. Correct? So that's called the parameter values for a model. Okay, so the data given here in our question was 7 chocolate cookies and 3 oatmeal cookies were the data given to us. And next is the model. We assume the process of a friend baking a cookie follows a certain probability distribution. In this case, Bernoulli trial for each cookie. It is either chocolate chip cookie or not. Okay, so why do we use Bernoulli here? Because there's just two. It could be a chocolate chip cookie or not. So let's say you put all this 10 into a black box. You put your hand in and pick one out. It would either be a chocolate chip cookie or a butter cookie. There is no other out of the two, provided that there is at least one cookie in the box. Okay, so next is parameter. The unknown probability of a cookie being chocolate chip. Okay, so we don't know whether it is chocolate chip or not, and for friend A, our parameter is 0.8 or 80%. We write it as 0.8 when we write it for probability and 0.4 for friend B. Okay, the likelihood function. So we saw this word even before. I said I'll explain it later. So now I'm going to explain it. This function, the likelihood function, which can be written as log of, L stands for log, of theta, which is the parameter, divided by x, which is the data. So we can read it like this. What is the probability that A made chocolate chip cookies or B made oatmeal cookies? So this is how we read it. So this is what theta by x means. So this function calculates the probability of observing our data for a given parameter. Our goal in MLE is to find that gives the maximum value of this function. So we are finding the maximum likelihood of that event to have occurred. Okay, as I said, we are not finding the value, we are finding the maximum value. Okay, so value could be A could have or B could have baked it, but the maximum value here is A must have, because we are talking about maximum. Okay, so also this is a note. Okay, when we solve the question I'll tell you, but remember that to make the max easy we often work with the log likelihood, because for example in Bernoulli, if you know the formula of it, it is the multiplication of the probabilities. So you know that probability is always less than 1. So let's say 0.1 to the power 3, that will be 10 to the power minus 1 to the power 3. So that will be 0.0001, which is a small number. So if I have to do 0.1 to the power 12, that's going to be 10 to the power minus 12, which is a very, very small number. So what we do is, to make the maths easy, we work with the log. So instead of P, if I work with log P, so that will be minus 12 log 10, which is minus 12. So the max is much easier when we work with log. So This is because the likelihood of many independent data points is their probabilities multiplied together, taking the logarithm turns the product into a sum, which is much easier to work with, especially when using calculus to find the maximum. This is also another case because log of 100 can be written as log of 10 into 10, and this can be written as log of 10 plus log of 10, which is log of 10 is 1, so 1 plus log of 10 is 1, so 1, so it's equal to 2. You can also write it as log of 100 can be written as log of 10 square, and this square can be taken out, so it can also be written as log of 10, which is also 2. Okay, so this is just to make the maths easier. So the general process of solving the question of MLE is this. Okay, so first you observe the data, okay, and choose a probabilistic model. So how to choose a probabilistic model is what we will be learning in the upcoming slides. But here, just remember the steps that is involved, and then when we do the sum, you will understand why we do this. Okay, first we observe the data and we choose a probabilistic model. Yeah, that you think generated the data. Okay, so we already discussed one probabilistic model, the Bernoulli trial or the Bernoulli distribution. So let's say I'm flipping a coin. How many trials could there be? It's either a head or it is a tail. So in this case, I can use a Bernoulli distribution because there's just two. So every event has just two outcomes. It's one among the two outcomes, right? So if there is a match which can either result in a win or a lose, what do we use? We use Bernoulli distribution. So for much other things, we will be learning what it is, but as of now, you already know how it works. Okay, so next is write down the likelihood function, okay, which is the probability of seeing all your data points given the model's parameter. Okay, so which is the probability seeing all your data points in the given model's parameter. Okay, find the parameters values that maximize this function. So first what you do is you write the likelihood function. Okay, so let's say I say a coin was tossed 5 times. Okay, it resulted in head, tail, and tail. Not 5, I'll say 7. Okay, head, tail, and then head, tail. Is there 7? Yes, there's 7. We will do this question once we read all the points. Find the parameter value that maximize this function. So what do we do to maximize this function? In maths, how do you find the maximum of a function? We find the derivative and equate it to 0. And then you solve it, you get the answer. Okay. So here, what distribution do we use? We just discussed, we use the Bernoulli's distribution. P of h as k and P of t as 1 minus k. Okay. So P is equal to, how many times have we tossed? So there is 1, 2 and 3 heads and 4 tails. So that will be k to the power 3 into 1 minus k to the power 4. So log of p is equal to 3 log k plus 4 log 1 minus k. So this is the probability, and we are going to find the maximum. So what do? We find the differentiation. So I'm going to do my d by log p divided by dk. So 3 divided by k plus 4 divided by 1 minus k, and we again differentiate 1 minus k and we get minus 1. So we get 3 divided by k minus 4 divided by 1 minus k. This is k. Okay, and we equate this differentiation to 0. So when we equate, we get 3 by k is equal to 4 by 1 minus k, and 4k is equal to 3k minus 3 minus 3k, and 7k is equal to 3 and k is equal to 3 divided by 7, right? So you can see here, based on our value, our sample space, there are 3 heads. So P of h is equal to 3 divided by 7 as given here, as we have derived from this maximum probability distribution, maximum probability estimation, and P of t is 1 minus 3 by 7, which is equal to 4 by 7. Understood? Yes. So next we are going to see the common types of probability distribution. First one we have already discussed, the Bernoulli distribution. Okay, so this represents a single event where it has only 2 possibilities, like a single coin flip. Okay, the parameter P is the probability, outcomes is success, and 1 minus P is failure. Okay, next is normal distribution. So normal distribution is when it describes a continuous bell-shaped curve and is often used for natural phenomenon like height or weight. It is defined by mean, which is the center of the peak, and its variance, which controls its spread. So we are going to see each of its type next. So at that time I will explain what mean is, what variance is, how variance determines the probability, how does it determine the graph, everything we will see there. Next is the categorical distribution. It generalizes the Bernoulli distribution for single event with more than 2 outcomes. So an example for this is dice. So in dice there are 6 events happening. So first is it could be 1, 2, 3, 4, 5 or 6. So it is pretty much same like the Bernoulli distribution, but in categorical distribution there is more than 2 outcomes. Okay, so when there's 2 you take Bernoulli, and when there's more than 2 you take categorical. So next is the Poisson distribution, where the number of times an event occurs within a fixed interval of space and time. So for example, in a call center, the number of calls a call center receives per hour. Okay, so per hour, the time is fixed per hour. So the number of calls is what we will take as the event. Okay, so here we take sigma as the parameter. So next is uniform distribution, where all possible outcomes within a certain range are equally likely. So uniform distribution we will see in detail when we are explaining its derivation. Okay, so first we'll start with Bernoulli. So as I said, you flip a coin n times, you get head k times. So we had just seen how we do the answer of derivation for it right here. Just now we had seen. Okay, so same here. Okay, but here we do it for n times. So with the use of Bernoulli distribution, you can with the help of this you can find it. So here we have another case, a cricket match. So read this. A cricket team plays n T20 matches, like x1 is equal to 1. So x1 is nothing but the probability is equal to 1 if they win a match, and x1 is equal to 0 if they lose a match. Okay, so it's like how we say head, tail. Here we are saying 1 for win and 0 for loss. Okay, So suppose they won k matches out of the n matches. The probability the team wins any given matches is, okay. So let us find the answer. So right now we just said, we know that P is the probability of them winning. So they have played k matches. So how do we write the Bernoulli distribution? P to the power k. And what is the probability of them losing the matches? Which is 1 minus P. Because we know that P plus something, okay, something, which is the lose percentage, is equal to 1. So 1 minus P is equal to something, which is the lose percentage. Okay, next is k. So what is the power? Which is n minus k. So they play n matches in total, k they win. So n minus k they lose, right? So now we find the log. So the log of P is nothing but k log P plus n minus k log 1 minus P. So now next this is step 2, and the step 3 we are finding the differentiation of it. So here log P is 1 by P, so k by P minus n minus k. Why do we do minus? Because here it is 1 minus P, so there's a minus here. Now we equate it to 0, so you get excuse me, k 1 minus P is equal to n minus k into P, and when you equate it, you get the MLE, the maximum likelihood estimation, as k by n, which is the maximum probability of the team, maximum likelihood of the team winning matches, maximum. Okay, so you might have a confusion between what is likelihood and probability. So for that, I will urge you to watch this video by Campus X. So this is the video. This is a very good video and you should definitely check it out. It's very, very useful and understandable. Okay. So next is the normal distribution. So we know that normal distribution is a bell-shaped curve and is often used for natural phenomena. Okay. So it is defined by its mean, which is the center of its peak, and its variance, which controls the spread. So which controls its spread. Okay, so here let me take a line. Okay, so what is the least value here? Least value is 160. Okay, and the maximum is 180. So 160, 165, 170, 175. I'll write 180 here. So what is the average of these numbers? It is going to be 170, but 165 plus 160 plus 170 plus 175 plus 180 divided by 5, which is 170. So 170 is the mean. Okay, so the maximum. So how do we draw the bell curve? Is it peaks at the mean and it is distributed this way. Okay, so this is the bell curve. So this is how you draw, and variance measures how spread out the data is. So there's a formula for variance, and that's how you find how spread out the data is. So if more number of values are concentrated at near the mean, then the bell curve will be peaked. So it will probably look like this. And if values are distributed, that is, if variance is low, then the bell curve will look like this. Understood? So this is what normal distribution is all about. So this is the formula of normal distribution. Okay, so this is nothing but 1 by sigma under root 2 pi to the power minus 1 by 2 x minus mu divided by sigma whole square. Okay. So for a normal distribution, this is the likelihood. So this is the likelihood, and we write it like this by removing the multiplying factor, and we put the n value to the top. So now we are going to take log on both sides. So by taking log, we get minus n by 2 log 2 pi. 2 pi is a constant, minus n log sigma minus 2 divided by sigma square summation n from minus 1 to n x of I minus mu the whole square. Okay, so we can write this as this or as square, doesn't matter, both the form is fine. And after this, okay, we have two possibilities. One is we can differentiate it with respect to mu, which is the mean value, or we can differentiate it with respect to sigma, which is the under root of variance. So we are going to take two cases for normal distribution, and then we are going to differentiate it. So first we are going to differentiate it with respect to mu. So the differentiation is very simple, it's just maths, you can follow it, and then you are going to equate it to 0. This is what you get after differentiation. And now we're going to equate it to 0, and on equating you get mu MLE is equal to, that is the maximum value of mu is going to be this, which is nothing but the mean value itself. So that's going to be the maximum value of mu. And next is we are differentiating with respect to sigma. So on doing that, you get this, and you're going to equate it to 0. We're not differentiating with respect to sigma, we are doing it with respect to sigma square. We are equating it to 0, and we get sigma square, the maximum value of sigma square can be this, 1 by n summation 1 to n xi minus mu to the power whole square. Okay, so now we can find this second derivative to confirm if this is the maximum. So if it is less than 0, we can confirm it as maximum. If it is greater than 0, we confirm it as minimum. So this is the concept of maxima and minima, local maxima, minima, which is a mathematical concept. So here we are finding the second derivative, and n is always positive and sigma square is also always positive. So minus of positive is always less than 0. So we can confirm that mu is equal to x bar, which is the average, is the maximum value of mu. Next, we are finding the second derivative of with respect to sigma square, and it is also less than 0. So we know that it is going to be maximum as well as for sigma square greater than 0. So this is our final result. So mu LE is equal to x bar, which is the mean, and sigma square of MLE is equal to 1 by n to the power summation 1 to n xi minus x bar the whole square. Okay, so this is for normal distribution. So next is the categorical differentiation. So from now on, I'm not going to explain the mathematical part in detail, because it is just following the same 3 steps, which is first you find the likelihood function, and then you find the log likelihood, and then you find the first differentiation, and then you equate it to 0, and then you find the value of maximum likelihood estimation. Okay, so for categorical distribution, I said that it is more than 2 values. So a good example is the roll of dice. So here you can see I have rolled the dice 60 times, and out of 60, 8 times it was 1, 10 times it was 2, 9 3 4 11 times it was 4, 12 times it was 60, and 10 times it was 6. So the probability of it being 1 is equal to 8 by 60, 2 is equal to 10 by 60, 3 is 9 by 60, 4 is, I'm doing nothing, I'm just getting this value and divided by the total number of times. Okay, so is 11 by 60, 5 is 12 by 60, and 6 is 10 by 60. So if you do the summation of all of this, you will get it as 1. It is for sure. Okay, so now we are going to find the distribution. Okay, we are going to find the derivation for MLE for a categorical distribution. So here, think of it that it classifies the penalty kicks into 3 categories: left, right, and center. So if this is the goalpost, so I'm cutting it into 3. So this is the left, this is the middle, and this is the right. Okay, so out of this, okay, so NL times it goes to the left, NC times to the center, and NR times to the NL, NC, and NR, right? And after this, theta L, theta C, and theta R are the probabilities of it going to L, that is the left, right, and center. So the likelihood formula is theta L to the power NL into theta C to the power NC, theta R to the power NR. It is nothing but the probability of it going to the left to the power of number of times it went into the left side, probability of it going into the center and the number of times it went in the center, probability of it going to the right and the number of times it went to the right. So that's the power. Okay, so we are finding the log, writing it this way, right? So we're writing it this way, and we know this constraint that the probability, the summation of probability is equal to 1. So via Lagrange's multipliers, we define this, and then we find the partial derivative, we equate it to 0. Similarly for center and for right. So we know that theta L, that is the probability of it going to L, is nothing but the number of times it went into the left side divided by the total number of times. So for example, I kick a ball 30 times and 7 times it goes in the left, 20 times it goes in the center, and 3 times it goes in the right. So the maximum probability, the likelihood of it going into left is nothing but PMLE for left is nothing but 7 divided by 30, for right is 20 divided by 30, for center, and for right it is nothing but 3 divided by 30, and the sum of all this will be equal to 1. Okay, so this is what we are doing here. And next is the final one, is the Poisson per goal match. So Poisson distribution is nothing but you can see here, we'll see, go to the scenario first. A call center receives an average of some calls per hour, but we don't know how many. So over 5 hours, the number of calls observed were 3, 4, 2, 5, and 6. So in hour 1, 3 calls, in second hour 4, third hour 2, fourth hour 5, and fifth hour 6. Okay, so this is what we do. This is what we say per duration of time. Okay, so this is the formula for the likelihood formula. Now we find the log of it here. Okay, and we differentiate it with respect to sigma, and after that we equate it to 0, and on equating we get the MLE value as x bar, which is nothing but the mean of it. So here, what is the mean? So 3 plus 4 is 7, 7 plus 2 9, 9 plus 5 is 14, 14 plus 6 is 20. So 20 divided by 5 is nothing but 4. So on an average, they get 4 calls per hour. Okay. Next is the uniform distribution. So here, you're a cricket coach. So you're a cricket coach running 10 batting practice session. In each session, players try to hit as many runs as possible in an over. Each session, the highest score is recorded, x1 to x10. Okay. So it doesn't matter which player hits. So they are just saying irrespective. So for example, let's say in first batting session, Virat hit x1. x1 is the maximum number of runs which Virat hit. x2, it is not necessary that Virat should have hit. It could have been Dhoni who hit it, or it could be Sehwag who hit it. So that's what we do, and we have it for a period of 10 times. Okay. So we know that the score can range from anywhere between 0 runs up to a maximum score of theta. But we don't know exactly what this value theta is. Maybe the maximum, it was a very tough ball. The bowler was too good on one day, or the pitch was good and they couldn't hit good runs. So probably they only hit 20 runs or something. Or probably it was a very good over for the batsman. It was someone like Yuvraj at the with the bat, and he hits 6 sixes, so he could get 36. So you assume the scores are equally likely anywhere between 0 to theta. Okay, that's called a uniform distribution. So my goal as a coach, so my as in you as well, so is to estimate what true possible score theta could be based on only the 10 scores that I have observed. So I have the maximum, and from that I'm going to estimate what could be the value of theta. So in this, okay, so this is the formula for uniform distribution. So it is going to be theta. Theta is nothing but the unknown maximum possible score. So it's going to be theta to the power minus n, or nothing but 1 divided by theta to the power n, if theta is greater than maximum of xi. Okay, so xi can be from 1 to 10 in our case. Okay, and it is going to be 0 if theta is less than maximum of xi. Okay, so we are going to find, so it's nothing but minus n log theta, as you can see from here, and we find the differentiation. We get n divided by theta, so n divided by theta, so theta minus n is equal to 0 and n is equal to 0. So there is no interior stationary point, so the log likelihood is strictly decreasing. So what we can say is the maximum value is what the maximum value of xi is. So let's say I have 10 players who hit 30, okay, 12, duck out, 7, 6, 7, 30, 10, 12, 15, 6. Oh, I think I wrote more than 10. 5 here and then this 5 here. Okay. So what is the maximum? So the maximum theta value is going to be 30, because that's the maximum anyone has hit. It could be twice, it could be once. So if it's 31 and 30, answer is going to be 31. So this is what MLE is all about. I hope you understood it, and if you did, please solve more questions on this concept for better understanding. And if you have any doubts, do ask down in the comments below. Thank you.